Welcome to the lecture titled Design of Controllers for the Advanced Smith Predictor. In this lecture, we shall discuss about the design technique for the controllers of the Advanced Smith Predictor proposed by Majhi et al. In our last lecture, we have seen the structure for the Majhi et al.'s modified Smith predictor and controller. There were three controllers in the structure. Now, the structure has been reproduced once more, where the servo controller or servo tracking controller GC is also connected in parallel with a relay. The main objective of the relay is to identify the dynamics of the real time process. So, once the dynamics of the real time process is obtained, then that is now shown by the transfer function model Gm e to the power minus theta m s. The advanced Smith predictor has got the three controllers GC, GC1 and GC2. Initially, a relay is connected in parallel with the controller GC for inducing limit cycle signal, and using the limit cycle data and the state space based exact analytical expressions we have obtained earlier for estimation of parameters of a transfer function model for the dynamics of a real time system. The Gm e to the power minus theta m s or the time delay theta m and parameters of delay free part of the transfer function model Gm are obtained. Next, GC1 in the figure has a major role for an unstable and integrating plant. The GC1 stabilizes open loop unstable integrating plants. Of the three controllers, GC1 in the inner loop is provided to stabilize open loop unstable process or integrating process. Also, it can relocate the positions of poles of stable processes. The other two controllers, as I have said earlier, GC and GC2 are used to take care of servo tracking and disturbance rejection by considering the inner loop as an open loop stable process. What we mean by that? With the help of GC1, we are getting some modified process, and we assume that modified process to be a stable one. Assuming that we are as if dealing with a stable process, GC and GC2 are designed to improve upon servo tracking and disturbance performances. Now, how the tuning algorithms or the formulae for or the technique method for designing the three controllers are done will be explained now. The closed loop response to set point and disturbance inputs is given by Ys is equal to Yrs Rs plus Yls Ls, where Yrs is the transfer function which is given by Gc e to the power minus theta s upon 1 plus Gm times Gc plus Gc1 times 1 plus Gc2 Gm e to the power minus theta m s upon 1 plus Gc2 G e to the power minus theta s plus Gc times G e to the power minus theta s minus Gm e to the power minus theta m s. The detailed derivation is again avoided here. Already we have discussed that with the use of signal flow graph, it is not difficult to obtain this expression Yrs. Now, Gm e to the power minus theta ms and G e to the power minus theta s are the transfer functions of the plant model and the plant. And please keep in mind, Gm is the delay free part of the transfer function model. As is evident from this denominator, under model matching condition, as you see in equation number 2, one part of the denominator will get eliminated or removed, thus giving us a relatively simpler expression for YRS. Similarly, YLS, the response or the transfer function between the output to the load disturbance can be given as YLS is equal to this much, as shown in equation number 3. Now, based on the assumption that Gm is equal to G and theta m is equal to theta, equations 2 and 3. What is equation 2? You see the equation 2 here. So, equation 2 and 3 reduced to YRS is equal to GGC e to the power minus theta s upon 1 plus G times Gc plus Gc1, and YLS is equal to G e to the power minus theta s upon 1 plus G times Gc plus Gc1 into 1 plus G Gc plus Gc1 minus G Gc e to the power minus theta s upon 1 plus G Gc2 e to the power minus theta s. Please look at equation number 4 carefully. The denominator is now free from any time delay term, and that particularly facilitates in designing controllers for the advanced Smith predictor control structure. Also, please see that equation number 4 and 5 shows us that we have got two different denominators. The denominators of equation 4 is different from that of the equation number 5. The equation 4 does not have a term like 1 plus G Gc2 e to the power minus theta s in the denominator. Therefore, the two responses, the set point response and the disturbance response, are decoupled from each other. What do we mean by decoupling of the responses? One response does not affect the other, or indirectly speaking, the controller you have designed for set point or servo tracking will not get affected by that from the controller you have designed for disturbance rejection. Also, when Gc2 equal to 0, that means when we do not have the disturbance response controller, particularly for unstable process, YLS will give unbounded output. That you can make out provided you substitute G, Gc, Gc1 by some transfer functions. Equations 4 and 5 again show that the stability of the advanced Smith predictor depends on the roots of the characteristic equation 1 plus G times Gc plus Gc1 times 1 plus G Gc2 e to the power minus theta s is equal to 0. Particularly, if you look carefully equation number 5, it has the denominator having the characteristic polynomial given over here or the characteristic equation given in equation number 6. Earlier we designed controller Gc and Gc1 based on equation number 4. Since the roots of the factor 1 plus G Gc plus Gc1 can be placed properly by the standard form based design, which we are going to discuss after some time, the optimum phase margin approach for design of a proportional controller for a time delay process that has a single right half plane pole can be used to find the parameter of GC2. So, basically equation number 6 has got 3 controllers and those are GC, GC1 and GC2. Design of GC and GC1 are done with the help of standard form, whereas GC2 is obtained using some optimum phase margin criterion. Consider the case of an unstable first order plus date time process. The process can be given by GPS is equal to k e to the power minus theta s upon T1 s minus 1. Now, I will design the controllers, 3 controllers for this unstable first order plus date time process. Let us select the form of the controller GC as a PI controller having GC equal to Kp plus Ki upon S. Now, GC1, the stabilizing controller, is a proportional controller given by GC1 is equal to Kb and GC2 is equal to Kl. Please keep in mind this is not Ki, that is GC2 is equal to Kl. Now, when you substitute GC, GC1, GC2 and GC and GP, then the delay free part of equation 4, please look at the delay free part of equation 4 means e to the power minus theta s will not be there, we will have G GC upon 1 plus G times GC plus GC1 will yield an expression of the form YR dash S is equal to K Kps plus K Ki divided by T1 s square plus K Kp plus K Kb minus 1 times S plus K Ki. Now, how to obtain this in the standard form? If you divide the numerator of equation 8 and the denominator of equation 8 by the term K Ki, then you will get another expression which can ultimately be expressed in the normalized form as YR dash Sn is equal to C1 Sn plus 1 divided by Sn square plus D1 Sn plus 1, where C1 is equal to beta times Kp divided by Ki and D1 is equal to Kkp plus Kkb minus 1 times T1 beta inverse. Okay? So, this is how we have obtained a standard form, we have obtained a standard transfer function YR dash Sn with the help of the normalization with beta equal to square root of Ki upon T1. So, basically the dynamics of equation number 8 and equation number 9 are not different from each other. Of course, there is a scaling factor because you are getting a normalized frequency now in place of the normal frequency of operation. So, it will be merely scaling of the responses you will have corresponding to this normalized transfer function. Now, we have got the optimum values for the coefficient of the standard transfer function D1 and C1. So, the standard transfer function given by equation number 9 has got 2 coefficients, one is C1 and another is D1. One can find optimum values of D1 corresponding to certain C1. So, for every C1 there exists some optimum D1 and with the help of some optimization function or with the help of some performance index, particularly the integral square time error criterion that is given by J1, it is possible to get optimum values for D1 for different values of C1. So, this plot shows the optimum values for D1 given by the dotted line for different values of C1 given by the x axis. So, C1 is varying from 0 to 8 and D1 is having different values when C1 assumes values from 0 to 8. Also, this figure shows the J1 value when the ISTE, integral square time error criterion optimization, is used to find the values for coefficients D1 and C1. So, this figure basically shows the optimum values of J1 and D1 versus C1 for some transfer function T1 to S. What we mean by T1 to S? YR dash Sn is equal to T1 to S is equal to C1 Sn plus 1 divided by Sn square plus D1 Sn plus 1. Now, what benefit do we get from getting the delay free part expressed in this standard form? Then we can find the values D1 corresponding to or for certain C1, and we can make use of beta C1 D1 to estimate model parameters of the controllers GC, GC1 and GC2. For the given plant parameter K and T1, we have got the plant dynamics given by equation 7. Please keep in mind the plant parameters are K, theta and T1. So, for given K, theta and T1, particularly for the given plant parameters K and T1, a higher value of beta results in a faster response to a step input if Ki is large. If Ki is large, a large value of Kp increases initial control effort. As you know, higher proportional gain not only increases the control effort, rather can leads to unstable or unstable operation or instability in the closed loop system. For that, we will constrain the Kp value to unity, so that selecting a small value for Kp upon Ki or selecting a small value for Kp upon Ki or indirectly speaking 1 upon Ki, a higher value of beta is obtained. Then D1 is obtained for the C1 value from the IST standard form and Kb is obtained from equation 11. So, 11 has got unknowns like Kp and Kb, because all other things are known, and of course, beta is, or we are choosing beta that way. Since Kp has been constrained to 1, the only unknown that is in equation number 11 is Kb, which can be estimated easily provided we have certain value for D1, provided D1 is known. Now, using this, the steps have been explained now the way you should proceed with to design the controller parameters. The controller GC2, prior to that what we have done, the steps for designing GC and GC1 are given in the steps 1, 2 and 3. Okay? The steps for designing GC and GC1 are given here, whereas for designing the remaining controller GC2, we have to resort to some other technique. The controller GC2, whose job is to reject load disturbances, is designed on the basis of stabilization of the characteristic equation 1 plus G GC2 e to the power minus theta s. Now, substitution of G and expression for GC2 gives us an expression 12 or equation 12, which has got the expression 1 plus K K L e to the power minus theta s. Please keep in mind in the upper in the numerator of this expression you have got k l not k I. 1 plus k l e to the power minus theta s upon T 1 s minus 1 is equal to 0. Now, based on the optimum phase margin criterion, now how can you find the optimum phase margin criterion, or how can you use the optimum phase margin criterion here? Again, get this expression expressed in the form of the frequency domain expression, and then you can find the phase angle of this function, whole function 1 plus k l e to the power minus j omega theta upon j omega T 1 minus 1, then optimize that phase angle with respect to the frequency omega, and then you will get a condition, and that condition will be obviously k l is equal to square root of T 1 upon theta k square. So, the equation in 12 will have optimum or maximum phase angle provided k l is equal to square root of T 1 upon theta k square. It is not difficult to obtain this expression 13. So, based on the optimum phase margin criterion for the stabilization of unstable first order plus dead time process, we obtain the parameter of the controller GC2. But this controller is designed with a constraint given by theta upon T 1 less than 1. The normalized dead time of the unstable first order plus dead time process has to be less than 1. If it is not so, then the formula given in equation 13 may not be correct. Let us go to case study 1, where we consider an unstable first order plus dead time system with steady state gain k equal to 1, time constant T 1 equal to 10 and time delay theta equal to 5. The normalized dead time theta upon T 1 is 5 upon 10 is equal to 0.5, which is less than 1. Therefore, there will be no difficulties in designing the controller GC2. Since beta is equal to given by square root of 0.1 times k I, how do you find this one? We know beta is equal to k I divided by T 1. Okay? So, when k equal to 1, T 1 equal to 10 and k p equal to 1, then beta becomes square root of 0.1 times k I. Now, constraining k p to unity and choosing k p upon k I h 0.1 gives beta equal to 1. We are choosing the value of k I indirectly. So, that way the controller GC, which has got parameters k p and k I, has already been designed with proper choices for k p and k I. So, this shows that k I is equal to 10, which gives us ultimately beta is equal to 1, and from equation 10 we get C 1 equal to 0.1, because you look at equation 10, C 1 is beta times k p upon k I, and since beta equal to 1, k p upon k I is 0.1, therefore, C 1 also will be equal to 0.1. So, thus we get C 1 is equal to 0.1. Now, for this value of C 1, the corresponding value of D 1 from the figure, which figure? From the standard form, figure for the standard form from this figure. So, when C 1 equal to 0.1, we do get exact value of D 1, optimum value of D 1 as the value of D 1 as 1.347. Okay. So, D 1 is equal to 1.347. Now, equation 11 can be used to estimate the unknown parameter of the controller GC1, which is nothing but KB is equal to 13.468. And again from equation 13 we obtain KL, the controller that improves the disturbance rejection, is equal to 1.414. Thus, all the three controllers are designed where the PI controller has got the parameters Kp equal to 1, Ki is equal to 10, and now the second controller GC1 is equal to having value 13.468 and GC3 is having value 1.414. Okay. So, when these controller parameters are put and simulation is carried out, simulation of the modified Smith predictor structure with the unstable first order plus date time unstable process is carried out, we do get the response from a unit step set point input that is introduced at time t equal to 0 and a load disturbance L of magnitude minus 0.1 at time t equal to 20. So, we do get responses corresponding to the set point and disturbance inputs, and the responses are shown over here. Here we see that we have got a quite good acceptable time response for the controlled system or for the closed loop system. Why it is acceptable? If I look at carefully the plot, the overshoot is not beyond 10%, it is rather quite low. The overshoot is less, the rise time is high, the settling time is also small. So, we have got all desired time domain performance parameters from the closed loop system, and of course, the disturbance response is not satisfactory, not so satisfactory as it is for the set point input response. Let us go to the case of a second order plus date time process. We will attempt to design the three controllers GC, GC1 and GC2 for this second order plus date time process, where we can have stable or unstable poles. With the controller choice of GC is equal to Kp plus Ki upon S, GC1 is equal to Kb plus Kds. Please see the difference. Now, we are using the stabilizing controller as a PD controller. So, the stabilizing controller GC1 has got derivative action as well. So, it assumes the form now GC1 is equal to Kb plus Kds, and the disturbance rejection controller takes the form of GC2 is equal to KL times TLS plus 1. Now, the delay free part of equation 4 YR dash S can be written as Kp upon Kis plus 1 divided by T1 T2 upon Kkis cubed plus T1 plus minus T2 plus Kkd upon Kkis square plus Kkp plus Kkb plus minus 1 divided by Kkis plus 1. How do you get YR dash upon S? YR dash upon S is given by the delay free part is given by the ratio of GGC upon 1 plus G times GC plus GC1. Okay. When you substitute those G, GC and GC1, then the delay free part becomes this one as shown in equation number 15. Now, normalization with beta is equal to Kki upon T1 T2 cube root gives the standard third order transfer function YR dash Sn is equal to C1 Sn plus 1 divided by Sn cubed plus d2 Sn square plus d1 Sn plus 1, where C1 is equal to Kp upon Ki times beta, d2 is equal to T1 plus minus T2 plus Kkd upon T1 T2 beta, and d1 is equal to Kkp plus Kkb plus minus 1 divided by T1 T2 beta square. So, 16, 17, 18, 19 gives us the normalized third order transfer function involving 3 coefficients, and the coefficients are C1, D2, D1. Like the earlier case, with the optimization of IST criterion or with the use of ISTE criterion, with the optimization of the function, it is possible to obtain optimum values for D2 and D1 coefficients with respect to C1 or for various C1. How to obtain optimum values for the coefficients for different order of transfer functions have been already discussed in one of our lecture. You need not worry. Simply you have to transport the final plot you have for either second order or third order standard transfer function. Now, I will explain you the procedure, the way we will design the three controllers. So, initially constraining Kp to 1, again where do we constrain Kp to 1? To reduce the control effort, and choosing a smaller value of Kp upon Ki, a higher value of beta is obtained. I believe you are getting this concept, why we are going for a higher value of beta. Now, D2 and D1 are obtained for the C1 value from the standard form given by the IST criterion. So, I am not going to show you further one plot. Now, directly the D2 and D1 values for a given C1 will be used in our further analysis. Thus, the design parameters of the controllers GC and GC1 are obtained using what? Using of course 17, 18 and 19, and with the choice of a smaller Kp upon Ki. Again, if you look at the denominator of the expression for y upon Ls, as I had said earlier, 1 plus g Gc2 e to the power minus theta s, this is to be stabilized when g is having unstable pole. For stabilization, what you have to do, a simple technique can be employed. When you write the expression in detail, which gives us now 1 plus KKL times TLS plus 1 e to the power minus theta s upon T1s plus minus 1 times T2s plus 1 is equal to 0. With the choice of TL is equal to T2, one term in the numerator and denominator will get cancelled. So, cancel TLS plus 1 and T2s plus 1 with the choice of course, T2 is equal to TL or TL is equal to T2. Then it will render again as a characteristic equation of the form 1 plus KKL e to the power minus theta s upon T1s plus minus 1. For stable processes, you need not worry, we do not use the controller GC2. So, the parameters KL, TL are 0, but for unstable process what will happen? We will get the characteristic equation now in the form of 1 plus KKL divided by T1s minus 1 is equal to 0. Then the way the parameter KL is obtained is already explained to you earlier, and that has been given in equation number 12. So, the optimum value of KL given by this expression KL is equal to square root of T1 divided by theta k square will be used in this study as well. Now, I will go to a specific transfer function of the process which is having the steady state gain, 2 the time constant T1 as 10, the second time constant T2 as 2 and theta equal to 3.5. Now, constraining Kp equal to 1 and Kp upon Ki is equal to 0.1, then beta becomes 1 and consequently C1 becomes 0.1. Then corresponding to this C1 we do get optimum values for the coefficients D2 and D1 which are found to be 1.487 and 2.046 respectively. Then we shall make use of the expression 16, 17, 18 as I have said you 17, 18 and 19 to estimate the unknown parameters of the transfer function model. Now, equation 19 gives Kb is equal to 19.963 and equation 18 gives Kd is equal to 10.867. So, also from equation 21 Kl is equal to 0.845 with of course with the choice of TL is equal to T2 is equal to 2, then only there will be pole 0 cancellations and ultimately rendering the second order expression into the first order, thereby by enabling us to make use of the optimum phase margin criterion to find the parameter KL. So, the parameters of the controller GC1 are KB and KD and the parameters of the controller GC2 are KL and TL are thus obtained. The magnitude of the step load disturbance L is now minus 0.1 and the response of the controller setting is compared with the response obtained using a popular method suggested in the literature and shown in the next figure. Now, in this case study 2, the solid line shows the responses obtained from the advanced Smith predictor and controller by Maggi et al. Whereas, the dotted one shown in this figure is obtained by some popular Smith predictor and controller method. Okay. The responses show that the design method and the advanced Smith predictor controller proposed by Maggi et al. Are far superior to that of the other Smith predictor controllers as far as controlling an unstable second order plus dead time process is concerned. So, as far as controlling an unstable second order plus dead time process is concerned. Okay. This is the beauty of the advanced Smith predictor controller, but the control design technique is not complicated, it is quite straightforward. You do have very limited number of analytical expressions and make use of those simple expressions can yield all the parameters of the controllers in the advanced Smith predictor controller. Now, another figure is shown here. The description about the figure let me give now. Another figure is given to show the superiority of the given method and that there is no restriction on the magnitude of dead time as far as the set point response is concerned. Whereas, there is the constant theta divided by T1 less than 1 for a satisfactory load disturbance rejection. So, controller settings for the next figure are Kp equal to 0.1, Ki equal to 10, Kb is 5.017, Kd is 3.408, TL is equal to 2 and Kl equal to 0.707, when the theta is 5 and Kl is equal to 0.674, when theta equal to 5.5. What we have done basically, why there are two thetas here? Now, we have assumed a 10% estimation error in theta. You are using some estimation technique. Suppose the time delay is estimated erroneously, there is estimation error of 10% in the estimation of time delay, then it can go to a value of theta is equal to 4.5 or a value of 5.5 depending on underestimation error or overestimation error. So, assuming that we have got overestimation, then in place of theta equal to 5, we will use theta equal to 5.5 and simulate and see what type of performances we do get from the advanced Smith predictor and controller. Now, the solid line again shows the response we had obtained earlier. Okay. This is the one we had obtained earlier. Now, the dotted line shows the robust performance in the face of variation in parameters of the transfer function model. And the two responses show us that we do get robust performances by the controllers, we do get robust performances provided by the controllers, although we do use very simple standard form based controller design technique to design the controllers. Okay. So, that is the beauty of the control, advanced control technique and the tuning algorithm schemes. Now, we will go to the case of a process with an integrator and a long dead time. Earlier, we have handled the control of unstable processes. Now, we go to the case of a process with an integrator and large time delay. For the integrating process, GPS is equal to k upon s e to the power minus theta s. When the controllers chosen are of the form Gc equal to Kp plus Ki upon s, Gc1 is equal to Kb and Gc2 equal to Kl, then the delay free part of equation 4 results in y r dash s is equal to k Kp s plus k Ki divided by s square plus k Kp plus k Kb s plus k Ki. Now, dividing both numerators and denominators by k Ki, we can get a second order standard transfer function. So, assuming beta equal to root of k Ki further results in a second order standard second order transfer function or second order standard transfer function of the form yr dash Sn is equal to C1 Sn plus 1 divided by Sn square plus D1 Sn plus 1. Again, where C1 is given by the expression C1 is equal to Kp upon Ki times beta and D1 is equal to Kkp plus Kkb times beta inverse. So, relatively simpler expressions than the earlier cases are obtained in this case, because we do not have any time constants associated with this process dynamics, or we do not have any time constant in the denominator of equation number 22. Now, how to design controllers, the three controllers for the integrating processes with long dead time. A higher value of beta is obtained again for a smaller value of Kp upon Ki. For the chosen C1 value, D1 is obtained again from the standard form with minimization of the IST criterion. The design value of Kb is obtained from equation 26. Kb, yes, there is the only unknown here. When we assume that Kp is constant to some value Kp equal to 1 and K is of course known and beta has been chosen. For the typical process now, the characteristic equation becomes 1 plus Gc2 e to the power minus theta s is equal to 1 plus Kkl times e to the power minus theta s upon s is equal to 0. Now, choosing Kl to give a phase margin of some specified value, suppose phi m phase margin is equal to 60 degree. That condition gives KL or gives an expression for the KL H. KL is equal to pi minus 2 phi m upon 2 k theta. Upon substitution of phi m of 60 degree, that means pi by 3, you do get in the numerator for KL H 0.5236, or KL is now given expressed as KL is equal to 0.5236 upon k theta. K theta are known to us, as you know, k theta are the parameters of the process or parameters of the process model. Now, in this case study, we will take the integrating process steady state process gain as k equal to 1 and time delay as theta equal to 5. With Kp equal to 0.1 and Kp upon Ki is 0.01, a further smaller value is used here. The normalization constant beta becomes 3.162. So, in this study we are going for a higher value of beta. So, higher value, this higher value of beta results in C1 equal to 0.0316. For this value of C1 further, using the second order standard transfer function, D1 is obtained as 1.336 for the standard form of the IST criterion. Equation 26 gives now Kb equal to 4.131, and from equation 28 using the phase margin of 60 degree, we do obtain KL as KL is equal to 0.105. Thus, all the parameters associated with the three controllers for controlling an integrating process are designed. Let us see the sort of responses we do get from the advanced Smith predictor, that is controlling an integrating process now. When the magnitude of the static load disturbance L is equal to minus 0.1, we do get the set point response that is given in the left hand side of this plot, and the load disturbance response given in the right side of this plot. Again, it is observed from this plot that we do get very or quite satisfactory set point input response, although the disturbance response can be improved upon further. Let me summarize the lecture now. So, the tuning algorithms have been developed for stable, unstable and integrating processes with long dead time. The tuning algorithms consider basically the standard transfer function forms and standard transfer function based controller design techniques. It is assumed that the transfer function model matches exactly with that of the original process dynamics. This is one of the major requirements we have for our analysis and controller design, and to design robust controller, we need to relax upon this condition. Now, simple controllers are designed based on the standard form and phase margin criterion. So, GC and GC1 are designed based on standard forms, and GC2 is designed based on phase margin criterion. It can be optimum phase margin criterion, it can be ordinary phase margin criterion. Any point to ponder? Can we use other methods to design the controllers? Yes, there exists numerous techniques such as the direct synthesis method, phase margin methods, optimal controller design methods, loop shaping methods, robust controller design methods and so on. Those can be used to design controllers for the advanced Smith predictor control structure. Thanks.